Hey, I've got here today another integral on the board. This one was suggested in the comments by Ryan. We have the integral from 0 to infinity of arctan x over x squared plus x plus 1 dx. And my very first thought looking at this was like, what is this x doing here? If I could just delete this. But then it's really simple because we have the derivative just sitting here of arctan, and we'd be done in like 2 seconds. So unfortunately, we can't get rid of this x, so we need to do something about that. And what I thought to do was actually a u substitution. And this u substitution maybe is not completely obvious. I'm going to substitute u equal to 1 over x. And even though we don't have the reciprocal in the bounds, this is actually often a pretty useful substitution. It's going to kind of work out very nicely, as you're going to see. Now with this value of u equal to 1 over x, I'm just going to solve for x. We'll have x equals 1 over u, and I'll take my derivative, and we'll find that dx is going to be minus 1 over u squared du. And then I'll just make this substitution. So plugging infinity, when x is going to infinity, u is going to be going to 0. And when x is going to 0, u is going to be going to infinity. Then in the numerator, we're going to have our arctan, but now x has become 1 over u here. And then for the denominator, we're going to have just 1 over u squared plus 1 over u plus 1. And then we'll have our dx value minus 1 over u squared du. Well, I'm just going to take this minus sign and bring it out front and use it to flip my bounds here. So we're going to go back to what we had originally, which is going to be 0 to infinity. And then I'm going to just distribute this u squared in. And as I do this, I'm just going to change the order just because I like it that way. So I'm going to multiply u squared times 1, and we'll have u squared. U squared times 1 over u is going to give us a u, and this last one's just going to be a 1. And then from here, all I'm going to do is just a variable change. I just want to change this back to x, because what I'm going to want to do is add this to the original integral. The original integral we'll call I. And because it's a definite integral, I'm okay at changing, because the variable name is not going to change the value of the expression or the area under the curve. Okay, so now that we have everything back into x, I'm just going to notice that we've just manipulated our original integral I into this integral that we can also call I. And what I'm going to want to do is just add this copy of the integral I and this copy together to get 2 copies or 2i. Okay, so now we've added the 2 integrals together. And again, that was just possible because we have the same bounds. We had the same bounds on both integrals from 0 to infinity. We had the same denominator, and we were all in x. And now at this point, this numerator may start to look a little suspicious, and we do have an identity for this. Let me just show you that right now. Okay, so we have this first identity on the board, arctan of x plus arctan of 1 over x is equal to pi over 2, and this is exactly what we have in the numerator. I actually did a video on the second form. We see that arctan x plus our cotangent of x equals pi over 2. And this works because arctan of 1 over x is actually the same thing as arctan of x. So with this first formula here, this is going to allow me to write my numerator as just pi over 2. And this is pretty convenient because this is a constant value. So what I'm going to do is if I rewrite my numerator as pi over 2, then I can just take it out front of the integral. So let's just rewrite this really quick. Okay, now at this point we're in pretty good shape because we got rid of all of our trig functions, and I think we're simplified quite a bit, but we still need to deal with this denominator right here. And what I'm going to do with this is I'm actually going to just complete the square on this. So to do this, what I like to do is let's just notice there's a 1 coefficient on the x here. So what I do is take a half of that 1, and we'll write this as x plus 1/2 and square it. Then if you multiply this out, you notice you get x squared plus a half x plus a half x is our x. Then for the last term, we're going to have plus a 4th. Well, we have a 1 here. So what I can do to correct that, we'll just add 3/4 on the end, just noticing that a 4th plus 3/4 gives us our 1. But in order to set this up, I'm actually going to rewrite my 3/4. I'm just going to write this as square root of 3 over 2. If I write this as square root of 3 over 2 squared, just notice that if you square that, that's just the same thing as 3 over 4. And what I'm doing here is getting this integral in the form of arctan. Let's just look at that formula really quick. Okay, so we have this formula down here in the bottom, and just notice this is exactly the same thing here. Like our a value is going to be this square root of 3 over 2 in this formula, and our u value will be this x plus 1/2. I'm not going to formally make the u substitution. We're just going to put it to use in this formula. Okay, so now integrating with that formula, we'll just have our pi over 2 out front. Then for 1 over a, it's just going to be the reciprocal of this, so I'm going to write this as 2 square root of 3. Then we're going to have our arctan, our u value, which is going to be x plus 1/2 over, and then we'll need this a value again. We'll take the reciprocal like this, and we'll have 2 over square root of 3. And we just need to evaluate this from 0 to infinity. Well, first, putting in the infinity in here, we'll have this pi over 2 times 2 square root of 3. So that's going to give me pi over square root of 3. So regardless of all this stuff, this whole thing's going to infinity. So arctan at infinity is going to be pi over 2. And then for our second piece, putting in 0, well, again, we're going to have this pi over square root of 3 in front. And then we plug a 0 in here. This x is going to be 0. We'll just have 2 times a half, which is 1. Arctan at 1 over square root of 3 is just going to happen at pi over 6. Okay, now from here, we just need a little quick cleanup. I'm just going to get a common denominator here. If I multiply this by 3 over 3, then we have this same denominator of 6 square root of 3. And then, of course, pi times pi is going to be pi squared. So combining these terms, the first one, we're going to have 3 pi squared in the numerator. Then we're going to have minus pi squared. And this is going to be all over 6 square root of 3. Then just calculating the numerator, we're going to have 2 pi squared here over 6 square root of 3. And we're almost at our solution, but remember this is 2 copies of the integral, so I'm just going to divide by 2 on both sides. We'll divide by 2 here and divide by 2 here. This 2 is going to cancel with this, and that's going to give us our final solution. This is just going to be pi squared over 6 square root of 3. So again, I just thought this was a really fun problem. Comes out nice. I like the pi squared. So thanks again for the suggestion, Ryan. Thanks everyone for watching today. Have a great day.